Um, so yeah, thanks everyone for being here. This is lecture number 2. So there's been a lot of questions about the waitlist. So we obviously have tons of interest in the class, which is really cool. As a result, we can't really favor any particular person on the waitlist, and so it's an automated procedure, and it's out of my control. Um, Now we do have the quizzes. So if you're on the wait list, then you're not able to join the Piazza or Canvas yet. So if you miss quizzes, then we'll drop up to 2 quizzes for people on the wait list. And then if you look at the grading for the course, you can have your lowest 3 quiz grades dropped. So in principle, you could, recover all of your grades even if you miss 5 quizzes if you're on the wait list. Um, if you get off of the wait list, then send the TAs and myself an email so that we can add you to Piazza and Canvas. And then finally, to get the quizzes dropped, please make a Piazza post, and we'll handle it through there. So we won't automatically drop the quizzes unless you make the Piazza post. Um, okay, so that's that's about the logistics. So now we can get into the fun part, which is the lecture. So today we're going to talk about neural text representation and classification. So we actually have a lot to cover today. Along the way, we'll kind of introduce basic loss functions that will actually come up throughout the course. We'll actually talk about uh, deep learning, some background on deep learning a bit. We do assume that you've, maybe seen some of this stuff before. So if it's completely, new or out of distribution, then perhaps like set aside some time to learn about things like PyTorch and automatic differentiation. But you'll kind of see that in the lecture. And then next class, we'll start talking about language modeling. And again, we'll actually use a lot of the ideas we talk about today. So it's a kind of nice progression. Um, so can I move this? Um, okay. So if you recap from last class, I introduced this really simple classifier called bag of words, and we represented the tokens as just these one hot vectors, and then took the sum, and that was our feature vector. Um, and we talked about some kind of symptoms that you observe with these models, which are like some things that are missing. We talked about conjugation or compound words, handling of word similarity. So a word like love versus adore. Handling combination features like don't love and don't hate. And then also handling sentence structure. So here's an example shown here. So this is the stuff we talked about in the last class. And today we'll cover kind of 4 different techniques. Well, actually 3, and the next class will be the 4th, for overcoming some of these. So first we'll talk about what are called subword models, which can help with this problem of conjugation or compound words. We'll talk about these continuous word or continuous token embeddings that can capture some forms of similarity, as well as do a lot of other things. And then we'll talk about neural network models, which again will give us various benefits, one of which is being able to capture these combination features. And then in the next 2 courses, actually, we will go over methods that kind of model full sequences and are able to capture sentence or, document level structure. So first we'll talk about subword models. And for this one, I probably won't have time to go through the full thing, but I put together this notebook. And the notebook's actually based on a really cool video by his name's Andrei Karpathy. So he's kind of a well-known researcher in machine learning, deep learning, and he has a really nice like teaching style. It's really hands-on. So you could check out the video, and then this is the notebook for our course, which is kind of based on it. Okay, so here the basic idea is we have our sentence, and we've been talking about words, and the basic idea will be to split these words up into multiple tokens. So here's an example. We have the, and we don't split up the in this example, but then we split up companies into these two tokens shown here. This is just visualized with this like underscore so that you can remember to put them back together. And then again, you might want to split up expanding. And you can see here that now this like ending is kind of chopped off. And so maybe we can have some like shared structure across different forms of the word expand. So again, the hope is that we will be able to share parameters. So if we have like a vector associated with each token, now the representation can possibly, share some parameters between these different word variants. And then also you can potentially reduce your parameter size and save on compute and memory. And this one might become clear once I kind of talk through the details. So it turns out that this idea of subwords, there's a kind of core underlying problem, and the problem is called tokenization. So the general problem is like we have some sequence of like raw text, and then we want to transform that sequence into a sequence of tokens. Okay, and so then the set of all possible tokens is called the vocabulary. And so you can see here that there's like multiple different strategies that you can use for tokenization. So one is the strategy of, splitting on just this white space, which is what we did last class. One would be the strategy that I showed you on the previous slide. I haven't said yet how to implement it, but that's one strategy. Another strategy is to, let's say, like tokenize by just selecting each character, and then you also have to have like white space as a token in your vocabulary. And so you can think about this for a bit, and some things that you want in your vocabulary or in your tokenization strategy. Well, first, we're going to use these models with a lot of different types of text, not only English text, but text from other languages. We want to be able to use them with like programming languages, basically, whatever's like on the internet even. And so we want our scheme to be expressive. So for example, if we only have like these English characters in our vocabulary, then we might not be able to represent Japanese, for example. And then you want the vocabulary to be efficient. So if you have a really large vocabulary, so let's say like every possible English word, every possible, Japanese kanji, then this just keeps growing. And now you have to like learn parameters for each item of the vocabulary. And that's going to be very, could be, inefficient. On the other hand, let's say we're just doing English and we teach and we choose a character level vocabulary. Well, now our sequences will be very long. Right? Like if you have a full document and you tokenize it into individual characters, then it's going to be very long. So in practice, you kind of want something in the middle. And so let's look at like what actual state-of-the-art models are doing in terms of tokenization. And so there's this cool website called ticktokenizer.vercel.app. And you can basically on the left here, like type in text and then select different tokenizers for different language models and see how things are tokenized. So like here you could do hello, how are you? And then maybe like types in Japanese. And you can see how it's tokenized by GPT-4. So here like hello got its one token. And then the question mark got its own token. And then it looks like, this character here got its own token, but then this one got grouped up. Okay, so this is like an example tokenization. Another interesting one is like numbers. So let's like write some numbers. And so it looks like the GPT-4 tokenizer is actually choosing to group every like subsequence of three numbers um, into a token. So actually, I wonder like, what if you just have a two-digit number? And then it looks like they have like specific tokens in their vocabulary for two-digit numbers too. Um, so let's look at how some other model does it. Let's say Code Llama. Okay, so does anyone notice any differences? Yeah. So it looks like they do this digit tokenization.
Two Japanese characters are separated.
Yeah, yeah. So now these are separated. Um, and then you can see that the token length is actually longer with this one as a result. Probably, I mean, yeah, it's splitting these and it's splitting the numbers. And so now you have more tokens. And so you can do this. Another interesting one is like with the older GPT model, if you write some Python code, then it will actually come up with individual tokens for each space. So it's like very inefficient with code. Um, but then let's take a look at Code Llama. Yeah, so here it groups two spaces into one token, for example. So maybe I was supposed to have a. Anyways, yeah. So you can see how they vary across different models, and then you get like different length sequences. You get like different handling of numbers and different languages and things like that. So kind of interesting. Um, so let's talk about how you actually do this in practice. So first you have to decide, well, so the overall idea is like we're gonna come up with some vocabulary and then start combining the elements into these subwords. And so the first step is like, what do you choose as your initial vocabulary? And so one idea is to use what's called UTF-8. So UTF-8 is there's kind of two steps. So one is you can express like any type of text pretty much using what is called Unicode. So you can go on if you want to read more about this, um, the Wikipedia for Unicode is kind of decent. And you can see here that there's essentially like 150,000 different Unicode characters. Okay, and so this will be expressive. Like you can express different languages, you can express code, whatever you want. And they kind of like keep adjusting it to ensure that almost everything is covered. Can anyone say a downside of using each Unicode character as your vocabulary? And I've actually already mentioned it. Mhm.
Size will be larger because individual token will carry like individual letter.
Yeah. So this is actually like the worst of both worlds because like your sequence length will be very long and your vocab size is at least 150,000. So we have to do something a bit better. And if you scroll down to this part of the Wikipedia, you could see that like Unicode text is actually processed and stored as binary data using some encoding. Okay, so basically like the computer is actually representing Unicode using just like bytes. And so the encoding that it uses is called UTF-8. And you can go down here and it basically is able to encode um, all possible like Unicode characters using just 4 bytes. And so what you have at the end is you have this like minimal vocabulary of just 256 um, possibilities for the for the byte. And then you can basically express any Unicode using this encoding, and then therefore like express any type of text. Um, so so it's kind of cool. Like you can here's some Python code showing that you can convert this string into these UTF-8 bytes. Um, and now you have this like really minimal vocabulary of 256. Okay, so now the problem is obviously that um, this vocabulary is just too small, and so our sequences are going to be like extremely long because now each like Unicode character is up to 4 bytes. So the second key idea, and this is the algorithm used in a lot of state-of-the-art systems, is called byte pair encoding. And so here the idea is going to be we start with some minimal, some base vocabulary, and then we have some training set. And then what we do is we like iterate over the training set and we find the most common token pairs. Um, and whatever is the most common, we turn that into a new token. So like we start out with 256, for example, we go over and find the most common pair, and then we add a token number like 257. And then we can like replace, uh, you know, 2 tokens with this new one. And then you just repeat the process, and it has the effect of like combining new tokens or merging tokens over time. So here's an example, and here I wasn't using UTF-8, I was just using characters to make it clear. But we have this training set, and it turns out that on the first iteration, the most common pair is E and space. And so what you do is you declare a new token, or maybe it was using UTF-8. And now you replace the text with it and repeat the process. So now like the next most frequent thing is T in space, then E and R, T and H, and so on. And so you build up these vocabulary of these kind of subwords. Mhm.
How was it that when you start explaining UTF, there were Unicode, there were like 150,000 options, and when you went to UTF-8, it dropped down to 256. What happened with the rest?
Yeah, yeah. So the idea is you can have this minimal vocabulary of these byte sequences, and then if you design some encoding procedure, then you can imagine like encoding each Unicode character using some sequence of bytes. Does that make sense? And so for any given Unicode, you can encode it using up to 4 bytes. Yeah. And so all you need are the bytes and then the like encoding scheme, which is called UTF-8. Yeah. Um, and so yeah. And so that's really the basic idea. And if you want to actually see like the code for doing this, it's fairly simple and it's in that notebook I mentioned. Um, but yeah, so that's the key idea. And then so there's a few practical tools that you can use for this tokenization. Might be helpful in like the projects and things like that. This one called Tick Token is written by OpenAI, and you can essentially like load their tokenizers that they've already trained. And then here you can see like encoding these different strings into different different tokens. This other one called Sentence Piece also supports training a tokenizer. So like you have some training set, like the example I showed, and then you can like train your own BPE tokenizer. Um, this has actually been around for a long time. So it turns out that they actually use Unicode as the base vocabulary. And then you can set this option to like if some Unicode character appears that's not in your merged vocabulary, then you fall back to the UTF-8 bytes. So these are kind of like uh, maybe a bit too much detail, but um, this library is actually very useful. And again, the notebook that I have actually shows you an example of like training the tokenizer, and it's just a few lines of code, so you can do it pretty quickly. Okay, so when you do this tokenization step, a really important thing is that the vocabulary that you get or the subwords that you get depends on the BPE training data. And so in particular, if you have like languages that are underrepresented and they're not in your training data, then these will never get like merged together. And so your sequences will be very long. So what people do in practice is to like make sure that the BPE training data is hopefully balanced. So like an example is for Code Llama, they probably made sure that a bunch of different programming languages are in their BPE training corpus. So then you can get this like really good tokenization. Also, as we saw, like these are somewhat arbitrary. So, like 1, 2, 3 could be tokenized in many different ways. There are techniques at like learning time to try to make your model more robust to different segmentations. Um, and then usually in order to like overcome some of these weird behaviors, you'll just hand define some rule. So actually, like the Code Llama paper that model that I showed you, they actually hand define this rule that like number tokens should always be just individual digits. Mhm.
Sample underrepresented languages.
Yeah, so let's say you have some training data and you're about to run like sentence piece on the training data. And let's say it has like one Japanese document and 10 English documents. Well, then you can like just like repeat the Japanese document if you want. Um, or probably a more realistic thing is like you have tons of data and then you have to decide what to put in your BPE training set. Then one way to do it is just like uniformly sample documents and then put them in your BPE training data set. Another is to like sample them such that the different, languages are equal in the, yeah. Mhm. Yeah, so I mean, it's going to be like a case by case basis. So some of the times it's a fairly large data set, and so you have to make these kind of coarse-grained just categories, you know, either based on like language or yeah, math data or different types of code. Hmm.
Previous slide,
Hmm.
multiple segmentation slide in China.
Yep.
Yeah, that statement, subword localization samples. I don't understand what that statement means.
Hmm.
What exactly does that line mean? Could you show some examples?
Yeah, yeah. So this, I mean, like one option was to like not include this line in the lecture because yeah, like the point wasn't to like fully describe their method, but it just gives some sense that like there has been research done to make the model more robust to different segmentations. So like concretely what you might do is like in your training data, just segment multiple ways and then train the model on like multiple segmentations.
Effectively, they hand-coded various segmentations during the training time. So they ensure the model is able to handle no matter what segmentation Goldman is able to work with it. How does that differ from not doing byte-time coding in the first place? Like if I'm handling using multiple segments, then it's the same as me not having done VP in the first place, right?
Not necessarily because like if you don't do BP in the first place, then you don't have any subwords.
That's what it's not scale.
Yeah. Okay, cool. So just as a recap, the tokenization and subword stage is really important in basically like when training any NLP model. Um, you have to think about how we represent the textual sequences. And so the method I described um, builds up this vocabulary based on the frequency of tokens in the corpus. Okay, so next we'll go to continuous word embeddings. Um, First, any other questions on tokenization before we do that? Okay. The questions have been really great. So yeah, keep them going. So here we actually have another code example that you could check out. And yeah, let's get started. So the basic idea here is instead of representing tokens using these one hot vectors, you might call these sparse vectors, we're going to have these dense vectors or continuous embeddings. So here, what we have is for each token, you're going to have this vector in, we can call it like DM, like in RD. And so now our lookup procedure is like given a token, get this vector. And concretely, what you do is you have what's called an embedding layer. So an embedding layer is a matrix, and one dimension is your vocabulary dimension. So you have like all your different tokens, and then you have for each different token um, one of these vectors. And then when it says lookup on these slides, it just means like select the column corresponding to that token. So pretty simple idea. And then it's good to just point this out that like you can view this as multiplying this matrix by a one hot vector. It typically is like more efficient to just implement it using using like array indexing or something. But sometimes you'll see this pop up like this, and like conceptually it's kind of useful sometimes. So if you have these continuous vectors, then the next kind of step up from bag of words is called continuous bag of words. So now we embed our tokens and we get these different vectors. And we're going to, again, just sum them together. And now you get this new vector, and we'll call it a hidden vector, H. Then so this H is in RD, but you ultimately want to get different scores for the different classes in your classification task. So to get those scores, we'll multiply it, or we'll pass it through what is called a linear layer. And a linear layer consists of multiplying the vector by some weight matrix, and then adding some bias. So here, sometimes I'll flip, from like horizontal to vertical just to make things present easier. But here you have like your hidden vector in RD, and then you have this weight matrix in R K by D. Okay, so now you have this new architecture and it gives you scores. And then the parameters that we would want to learn is you actually want to learn these embeddings. You also want to learn the weight, the weights, and then you also want to learn this bias right here. Okay, so now instead of just this like weight vector at the end, we have like multiple learned components. And then if you haven't seen this before, here's an example in code of implementing this embedding layer. So again, you like declare some weight matrix. Here, this is writing this out with an actual like one hot vector, and then multiplying it by the weight matrix. Again, the code examples are not meant to be like efficient or anything like that. They're just meant to like make concrete, things on the slides and things like that. And in practice, this is implemented in different libraries like PyTorch as the embedding layer. Then you can define this continuous bag of words architecture pretty easily. So you have your embedding layer, you have the linear layer, the output layer. And then it's just like 4 different steps. So you embed the tokens, you sum them together. This is just like reshaping the dimensions, and then you pass them through the output layer. Okay. Everything good so far? Okay, and so now the interesting thing is like now we're in this continuous space. And so ideally, we would want like vectors that kind of have some notion of similarity. So if two words are similar in some sense, then maybe they'd be close in vector space. And then moreover, you can interpret this like high dimensional space, like each different dimension or each vector element could represent some feature. Um, right, and it's kind of up to the learning algorithm to learn some feature representation that is, ultimately useful in the architecture. Now, in reality, we'll set the dimension to be 512 or 1024. So you would actually have to use some visualization technique to, to put them onto a two-dimensional plot. I think in a later lecture in the course, I'll go into some visualization techniques. Okay, so that's the basic idea of having these token embeddings, where we represent the tokens as learned continuous vectors. So any questions on this part? Okay, cool. So next we'll talk about neural networks. So if you remember last class, we kind of ran into this issue of combination features. So if you have things like uh, don't love, nothing I don't love, and so on, you basically want to do these like more complex operations over, multiple parts of the sequence. And so one way of achieving, or like a good way to achieve this is through a neural architecture. And I'll talk about why in a couple slides. And so the next step up in complexity is called deep continuous bag of words. So we're going to start with our bag of words, like before, where we're summing things up. And then now we're going to have multiple layers. So it's going to be this like deeper neural network. And then at the end, again, have this linear layer that goes from the hidden dimension to the number of classes that we have. Okay. And so now the key difference is that, yeah, we have these multiple layers. We also have more parameters, right? So each layer here, again, has this like a weight matrix and a bias term. And then you can notice here that it has this tanh function. And so the question is like, why is tanh there? And what fundamentally is this doing different than the architecture I showed you before? Is it like the stacking? Is it, exactly what was written here? And so it turns out that like one really key thing is that introducing this function tanh, or in general, some other activation function, introduces a nonlinearity into the network. So all the operations that I talked about before, like a matrix multiplication or adding a bias, those are just linear operations. And so adding in the nonlinearity increases the like expressivity, so the like patterns or the functions that the network can model. And then the idea is like once you introduce one nonlinearity, then you're like doing a more complex transformation. And so if you start stacking these complex transformations together, then the whole thing like becomes very non-trivial. Okay, and so just to like drive this home, if you don't have the nonlinearity and you just stack two linear layers together, well, then that's actually just the same as just having another linear layer, because you're just multiplying, two matrices together and you get another matrix. Okay, so that's a kind of key thing that the deep architecture is giving us. And there's a lot of different activation functions. So sigmoid, ReLU is a popular one. And you can like take a look at this PyTorch list for some other ones. And throughout the course, we'll, when I'm introducing an architecture, you'll see like which activation it's using. Okay, so now to implement this in code, I guess I just made a one layer. There's like one hidden layer. but as an exercise, you could like turn this into a 2-layer or however many you want. And the only difference here is, now you add in this linear layer, and then in the forward pass, you're adding in, yeah, what I showed on the slide. Okay, and so now, when you think about this, like this network can start to learn these different feature combinations. So for example, like in the second layer, it's receiving inputs from the different dimensions of the hidden vector. And so one element in the hidden vector might represent some feature that's like related to not. And then another feature might be related to like positivity or negativity and hate. And so the second layer is able to like combine those and transform it into yeah, these kind of like nonlinear transformations of the features. So a bit of hand waving there, but hopefully you kind of get the sense of yeah, what we're getting with the neural model. So any questions on that? And then we'll talk about training and loss functions and things like that. Mhm.
Can you repeat why the single layer wasn't capable of capturing those relationships between the features?
Yeah, so the single weight matrix, I guess, would still yeah, it would still be able to compute a feature that's a function of like multiple hidden dimensions. Yeah. Um, and then the nonlinearity just allows you to represent like potentially more complex, more complicated features.
How does the model handle like combination?
Oh, yeah. So as I mentioned, if you like, as long as you have a weight matrix, then it will be doing some function that involves multiple hidden dimensions, and so that could actually be sufficient for some combination features. And then we don't know exactly like which one the nonlinear function is learning. We just know maybe that like it can learn more complicated things. Yeah. Okay. Um, so yeah, let's talk about training. And when we train a neural network model, so we use gradient descent, and there's kind of three different steps. So first, we write down a loss function. Then we calculate the gradients of the loss function with respect to the parameters. And then we adjust the parameters in the direction that reduces the loss function. So the gradient will give us like the direction of steepest ascent or descent, and then we just make sure that we like put the negative sign correctly so that we're reducing the loss function instead of increasing it. And then how you do how you actually perform this movement turns out to there's different strategies for it. So let me go through each three of these parts. So an example loss function, I'm going to go through two different loss functions. And the reason I'm going through these two is because they're very popular in practice. And so actually like the second one will be used in, most of the language models we talk about. And so I do think they're like really good to know. And even if you've seen this before, probably review. So the first one is called binary cross entropy. So here our task is just binary classification. So let's say we want to like classify tweets as either positive or negative. Well, then we can have our model output some number that we interpret as a probability of the positive class. Okay, so in order to be a probability, it has to be between 0 and 1. And does anyone know how to make a neural network output a number between 0 and 1? Like, how could we take the softmax and sigmoid? Okay. So yeah, softmax we'll use for multiple dimensions. So that'll be in the next slide. If you just have this like one scalar, then yeah, you can use what's called the sigmoid function. So the formula is here, and yeah, this just gives you some function that ensures that things are between 0 and 1. And then let's say that, we're training, and so we have some ground truth label of whether our tweet is positive or negative. So that'll be y either 0 or 1. So here's the binary cross entropy loss, and let me just like talk through it. So it's useful to look at like one label at a time. So let's say that the ground truth label is 1. Then that'll be this kind of yellowish curve here. And what happens to the loss is if y equals 1, then this part goes away. And so our loss is just 1 times the log of the probability score from our model. Okay, and then you can see that plotted here. And so it's basically saying like, okay, the ground truth label is 1, but if our model gives us a probability score that's low, then the loss is really high. So kind of intuitive idea. Like we want to penalize the model a lot if it's wrong. And then as its probability score is increasing, the loss is going to 0. Okay, and then the other case is basically like symmetric or something like that. So let's say y is 0. Now this term goes away, and now you have like a log 1 minus p, and this is what it looks like. So your model gets a high loss if it gives a score of 1, and a low loss if it gives a score of 0. Okay, so this is the binary cross entropy loss. And then we could think about like, what if you have multiple classes? So we might call this one just cross entropy instead of binary cross entropy. So now let's say that the task is to classify the tweet into positive, neutral, or negative. And it turns out that like what I'll say, it could be any number of classes. It could be like 50,000 classes. It doesn't have to just be 3. And let's say we're given some training example, X and Y. And so now our model outputs a probability vector. So does anyone know how you get the probability vector? Softmax, exactly, yeah. So here's softmax if you haven't seen it before. So you have these scores. Sometimes the scores are called, actually very frequently these scores are called logits, Logits. So you have to kind of get used to saying that word. And then the softmax transforms it into a probability distribution using the formula here. And so probability distribution just means that everything is between 0 and 1, and then the sum is 1. Okay. And so now we could view this ground truth label as like a one-hot vector. So here it's saying that the ground truth class is positive. And then the cross entropy loss looks like this. So it basically says, okay, sum over all of the different class dimensions. And then you have the log of the probability score from the model. And you can notice that like all of these will actually just zero out except for one of them. So it's this, yeah, it's basically saying like, what is the log probability of the target class? And so if we think about what this is doing, again, let's say that the model assigns high probability to the correct class. Well, then Pi will equal 1. So log of that will equal 0. And so you'll have a really small loss. So kind of makes sense. And then conversely, if you have a low probability assigned to the correct class, then it'll be near 0. And your loss will actually go towards like negative infinity. Okay, so kind of if you like think about it, then kind of intuitive idea. but like, where does this actually come from? And especially if we're going to be using it in language models and all this stuff, um, then yeah, we want some like deeper understanding. Um, so there's this idea in information theory called KL divergence, and it's some way of measuring the divergence between two different distributions. So like if two distributions are more similar, they'll have a lower divergence. If two distributions are different, they'll have a higher divergence. And then this is just like the formula. It's just the definition of KL divergence. Then you can do this like two-line simplification. So here it's just expanding out um, the log, and so now you have like two different terms. And then you can see that if we're trying to minimize this KL divergence with respect to the second distribution, then this term here actually doesn't matter because it's just constant regardless of what we choose P2 to be. So minimizing this is equivalent to minimizing this. And this is actually the cross entropy loss. Okay, so like as you minimize cross entropy loss, you're making two different distributions kind of closer to each other. So kind of nice idea. And so here in our example, your distribution is like one is your target vector and one is your model's probabilities. And so by minimizing the cross entropy, you're trying to bring those together. Kind of nice idea. I kind of like that one. And we'll actually see this argument come up when I talk about language models. It's slightly different form, but same idea. One more thing, then I'll pause for questions. So here's some code actually implementing the cross entropy loss. So nowadays, this loss is like so, popular. It's just implemented in the libraries and it's very optimized. Here's one possible implementation. Where again, you have the logits, which are like the scores. And then you do these two different operations. So if you haven't seen this before, then maybe go through and like, try to understand what's going on here. So does anyone have questions about loss functions before I go to gradients? Okay. Yeah, other thing is that like obviously these aren't the only two loss functions. There's many more. And so one thing you could do is like look in PyTorch and look at all of the different losses that are implemented there. And that'll give you some way of doing like a quick survey. Okay, so next we want to calculate gradients of the loss function with respect to the parameters. And so here I just want to warn you that like the next slide is a bit tedious, but it's motivating the idea later that after this slide, we'll compute these gradients automatically with things like PyTorch. But I do think it's like a good review, or if you haven't seen this before, we really want to see like the full optimization procedure. Okay, so now what we want to do is we have our we have our model, and we want to find the gradient of this weight matrix so that we can adjust it, so that we can lower our loss. And so let's say we have a really simple model, which is just like Wx plus b, and then you pass it through the sigmoid, like I mentioned before. And let's say our loss function is binary cross entropy, because this one will be like the least painful for computing the gradients. And then the key idea, like this is actually like really important. The key idea is that you're going to leverage this chain rule. And so what you can do is like you want to find the gradient of the loss with the gradient of the weights. And that expands out into these three different terms. So one of them is like the gradient with respect to P, which is kind of like the output of your network. Then you go one layer or one step kind of in the network and look at the gradient with respect to Z, which is this thing here. And then you go one step more and look at the gradient with respect to X. And so it's kind of cool that like yeah, you can just decompose this into these three terms. And then if you were to work out the details, then you could compute each one of these three terms. It turns out to look like this. This one turns out to look like this. And then this one's kind of simple. You're just finding the gradient of this with respect to W, which is just X. And then you multiply them together. Okay, and so now like if you really wanted to, you don't have to use PyTorch. You could implement this and now you have a loss function, you have some model, and you have the gradient, so you can do gradient descent. So the next step, as I mentioned, is we actually want to move the parameters in the direction that reduces the loss function. And the most basic thing you could do is stochastic gradient descent, like standard, yeah, SGD. And so here we get our gradient of the loss. And then we update our model's parameters by taking a step in the direction of the gradient. So here's our current parameters. We take this step. How the magnitude of the step is controlled by this, which is called the learning rate. And then you get some new parameters, and you can kind of like optimize your loss in this like iterative procedure. So like there's been different variants for doing this. I think it's in next class, I believe. I'll talk about one that is commonly used in practice called Atom. And one way to think about it is that like these different strategies are like implemented in your neural network library. And then you can like swap them out and sometimes get you know, better optimization dynamics than you get with this like simple SGD. And again, I'll show one example next time. So here's what this looks like in code. And yeah, if you haven't like seen something like this before, now you could have the loss just implemented. You could set up SGD as the optimizer, and then you could have this like training loop where you iterate through the training set. You get your logits from the model, pass it to the loss, and then yeah, take this step. So this is like the SGD step from the previous slide. So any questions about this? The next few slides will give some background on the automatic differentiation that's in things like PyTorch. Okay, cool. And again, yeah, hopefully you've like seen at least some of this at some point, because you will be training models in this class, and yeah, using these loss functions, and obviously using things like PyTorch. But yeah, so just for completeness, and I also think it's like pretty interesting. Um, what is actually going on in these libraries like PyTorch, and how do you actually think about a neural network, like representing it to the computer? Well, nowadays you represent it as a computation graph, and the computation graph will allow you to automatically kind of keep track of the execution of the network, and then efficiently perform the gradient computation so that you can optimize the network without having to derive the gradients by hand. So the key idea here is you represent your network as well as like any operations with it as a graph. So a node at the kind of leaf level is some kind of like data, like scalar, vector, matrix, or tensor. And then you can have these nodes which are operations. So here this node corresponds to the transpose operation. Okay, and you could have other nodes for like matrix multiplication, Yeah, things like that. And then the edge into one of these nodes represents the argument to the function. Um, and yeah, this bullet point's kind of saying the same thing. And then the key thing here is that like the computation graph knows how to do two things with each one of these function nodes. So first it knows how to um, actually like compute the function. So that's the kind of forward pass. So in this case, like you're actually performing the transpose on the input. And then it also knows how to compute the gradient of the function with respect to its input. Okay, and then the really cool thing is that, again, you can use this chain rule to basically use these local gradients, so the gradient of a particular node in the graph, and then basically like chain them together using the chain rule. So concretely, at this point of the graph, you'll have some like incoming gradient from the chain rule, and then you'll just multiply that with your local gradient that the node knows how to compute. And then through that, you can get like the gradient of the kind of end of the function with respect to this node's inputs. So again, like if you haven't seen this before, then you might it's a kind of concise slide, but this is like really the key idea that you have these nodes, they know how to perform the forward pass and the backward pass, and then you can kind of like chain things together due to the chain rule and compute gradients throughout your whole computational graph. Okay, so just to show like a little less more than one node, you could kind of build up this computation graph, and up here you could see the expression that it's representing. And here's a kind of complete graph, and at the end it's like taking the sum of these inputs, and then this is the expression that this graph corresponds to. Oops. And then, yeah, you could come up with like different variable names, and these are just associated with the like intermediate computations in the graph. So again, just to like drive the point home more, you have these different stages. So you obviously have to construct the graph, and then you perform this like forward pass or forward propagation. So here you start with the leaf nodes, and then you move up in this topological ordering. So here you would do these two. You could notice that like, you could possibly leverage parallelism somehow because you can compute both these at once. And then you do this until like every node has been computed. And then now you start the backward pass or back propagation, where you go in the reverse order and again calculate the gradients using the chain rule. So yeah, for example, here you would compute the gradient of this sum with respect to its inputs, and then you would start kind of propagating downwards in the graph. And for example, this node, you would take this incoming gradient that you just computed, and then you compute your local gradient, and then just multiply them together. And again, that's the kind of key idea. So now you can like go all the way down the graph and get whatever gradients you need. So really, yeah, really cool idea. And kind of like the availability of these graphs and libraries that can compute the gradients have really allowed people to experiment with different neural architectures. And you could imagine like at one point people were computing the gradients by hand. And so any like new loss function that you tried, you had to write out the gradients and things like that. And so this is really like part of helping deep learning take off. Let me check what is next. Oh, this is just a summary. So again, you create this graph, you calculate the result, And then if you're training, you do the backpropagation. So does anyone have any questions about this? Okay. So concretely, yeah, nowadays, these kind of ideas are implemented in different frameworks. And you can kind of realize these ideas in different ways. You also have different companies interested in these frameworks. And so as a result, there's like a few different options. So some of the major ones are PyTorch and TensorFlow slash JAX. So PyTorch is developed by, well, at the time it was Facebook. Now it's Meta. And TensorFlow and JAX is developed by Google. So TensorFlow was kind of first. I think it was around like 2016, 15, I want to say. And then JAX is a bit more recent. And these are actually Graham's slides, but I mean I agree with his takes. So the PyTorch is maybe like the most widely used in NLP. And you typically will see TensorFlow and JAX used in projects associated with Google. And so that's just like a like a Graham made this slide, so but I mean yeah, like roughly speaking, you do see a lot of projects in PyTorch. And then maybe you see a smaller number in TensorFlow and JAX. But they're both really cool and they actually offer different trade-offs. So PyTorch was built to favor dynamic execution. So maybe to say what that is first, let me talk about TensorFlow. So like TensorFlow, the idea was you declare upfront your entire computational graph, and then you just like send it to TensorFlow and it runs. And so the thing is that like one tricky thing is you have to kind of declare everything up front. You can't like, put a debug statement halfway and just like run part of the graph. You have to actually like build in some stuff to do that into TensorFlow, and it's kind of unnatural. Another tricky thing is like using control flow in Python. So if you have like a for loop, then you could just like use PyTorch to keep multiplying matrices together. But then doing that stuff in TensorFlow requires like, yeah, kind of building it into this like graph building procedure. So this often goes by the name of like dynamic versus static. And then JAX is kind of like motivated from a different programming paradigm. So PyTorch you can think of being like maybe like Python, so it's imperative. And then JAX is aimed at kind of like functional programming. So here again, you have some like upfront declaration, and then everything is kind of like a ideally like a pure function. So then this actually makes it really easy to parallelize things. So you'll often hear JAX come up in the context of like, yeah, parallelism. It also turns out to be easier to do higher order gradients. So if you need to take like the second derivative, third derivative. So you'll sometimes see JAX come up in like scientific computing applications, things like that. And then I mean I was kind of joking. It's also used to train even like really large networks and not only at Google. So that was a bit of a joke. Um, so yeah, I guess that's all there is for today. And like I said, there's a code notebook corresponding to this section of the lecture. And so you can go through and for whatever reason, for fun, to clarify the ideas, to see how this is done. It actually trains the task is classifying tweets. It actually trains a tokenizer, like I mentioned, with sentence piece, and then implements these different architectures that I told you about. So like continuous bag of words and deep bag of words. And you could see that the deep bag of words model ends up doing a lot better. So you can play around with that a bit if you want. So yeah, that's all there is for today, and I'm happy to take any more questions.